Hello and welcome to this tutorial. In this video I'll show you how you can use Houdini solver to create a gross effect like this one, which is part of the Houdini solver trailer video, or here is another example of using this solver for creating this kind of effect. In this tutorial, I use a simple geometry to have a faster feedback. So let's start with the simple geometry like a tube. And as you can see, the primitive type is polygon. And here I added more divisions. And here with the help of a normal node, I assign the normals to the points. And here is the unit cell that I'm going to use along with the need solver. And here this transform node rotates this unit cell 90 degrees along the y-axis to have a correct orientation for the final texture. And here is the result. If you have not seen the previous video on this digital asset, please go back and see that video. Basically, that video explains these parameters and how they work together. Here I connected the output of the digital asset to a fuse node, and I tried to connect the end one and end group of the unit cell. And again, if you don't know what are these two groups, please go back and see the part 1 of this tutorial. Okay, let's select a point from this geometry. For example, this point, and let's create a group and let's name it starter, and our effect will start from this point. And here let's create a delete node to delete everything but this point. So let's select the starter point, delete non-selected. Okay, and let's create a point, and let's create a color attribute for this point, and let's choose 1 for the red value. Let's create another point node and let's connect it to the group, and also let's add color attribute for this geometry and make all the points black. So here now we are able to use attribute transfer to transfer the red color attribute to the geometry. So let's select the points as the attributes, and let's select the color, and in the conditions tab let's decrease the distance threshold, and let's create animation for transferring the red attribute to the geometry. At frame 1 let's create a keyframe for distance threshold and the blend width, and let's start with the 0, and at frame 120 let's for example choose 4 for the distance threshold, and maybe 8 or 10 for the blend width. Okay, we can come back and change these values later. And let's create a delete node to delete the black points. So let's type an expression, and here let's type color red is equal to 0. So here is our simple animation for the gross effect. Here I want to add more complexity to this animation and to this effect, but generally the basic of this effect is this simple animation. So from now on we have to just add complexity to this animation. So here, for example, I can create a point wrinkle node and create a displacement for each point based on the color attribute and based on the normal attribute of the point. As you can see here, we have access to the normal attribute of the points. So let's here type, for example, position is equal to positions plus 0.5 multiplied by the normal attribute, and of course multiplied by 1 minus color red. So basically it means that if the color of the point is 1, the color red of the point is 1, this part of equation will be 0, and the position of the point is equal to position of the point. So the points will have their original position. So here let's check the results. Here you can see this gross animation, and of course you can increase or decrease this number to add more displacement to the points. But as you can see here, the animation is very uniform, so let's introduce a noise to the color attribute. So let's create a point swap node and let's dive inside, and let's create a anti-aliased noise, and let's connect the position to the position, and let's promote all these parameters of the noise. And let's add the output of the noise to the color attribute, so to the actually red value of the color attribute. So let's create a vector to float node. Let's connect it to the color, and we are interested in the red value, the first output. So let's create a add node and let's add it to the red color, and here we need a float to vector node to convert the value back to the vector, and let's connect the output to the color. Okay, here you can see the result, and let's connect this delete node just after the point swap node. Okay, and as you can see here, after adding noise to the red color attribute, most of the points now have a value higher than 0 or lower than 0. So first of all, let's correct this expression, and let's choose the color red is less or equal than 0. And the other thing is that we have to apply the noise only to the points that has the color red value attribute higher than 0. So first of all, let's create a group here, and let's choose group by expression, and let's point as the entity, and let's write here color red is greater than 0. Okay, and here let's choose the group 2 as the point group, and let me rename this group name to, for example, red points. Okay, red points. Okay, and for adding even more complexity, let's add a Repel node. Okay, let me connect it to the attribute transfer node so I can adjust the attributes, and then I can connect it to the delete node. So let me connect it to the group 1. Okay, here you can see the animation of the Repel. Let's decrease the frequency to 0.5, and also let's decrease the wave decay so we will have even more waves at the end of the tube. So, and also let's, for example, increase the scale of the ripples. Okay, and as the center, let's choose a position approximate to our starting point. So here is the starting point, and here let's choose a position near our starting point. Okay, and here as the direction, also let's select the direction which is approximately equal to the normal attribute of this point. So here, as you can see, I have to add the z value, that's not too much. Okay, now you can see the animation. Now let's connect it to the output of the point WAP node. Let's see the result. That's good, but we have to create an animation for the height and the scale value. So let's go to the frame 1, let's make a keyframe, and for example let's go to the frame 96, and let's choose 0 value for the scale and the height value and the height parameters. Okay, let me pause the video and catch the simulation. Okay, here is the cached animation, and as you can see here, we have a nice gross animation for this geometry. Okay, here before caching this animation, I just created an animation for this point, and for the color red attribute, as you can see, I created an animation for increasing the value of the color red within 24 frames, so it can help to have more smooth animation. And the other thing is that I've changed these values to have more interesting animation, the frequency and the roughness of the noise. Okay, so if you see more carefully here, you can see some black spots on the surface of the geometry. So what we have to do here is to create a parameter like here, like this part of equation 1 minus color red, to control the amplitude of the noise. So let's go inside the point swap and let's create exactly the same parameter. So let's create a subtract constant node, and let's connect it to the color red of the point, and the subtract parameter should be 1. So let's multiply it to the output of the noise. Okay, so now, like before, if the color red value of a point is equal to 1, the magnitude of this noise will be 0. So let's connect the output of the multiply node to the add node, of course, instead of this input. Okay, and immediately you can see now we don't have any black spot on the surface, and the only black areas are at the end of the animation, which we can correct them using the higher value for the blend width or the distance threshold. Okay, as you can see here, we have a little bit black color, so let's increase the distance threshold, for example, to 5. Okay, that's good. Now let's add the animation of these wires to the current animation. Okay, so let's create a curve here. And let's choose nerves as the primitive type, so we have more smooth curve. Okay, something like this. And also let's connect it to the resample node to convert it back to the polygon, and let's choose 20 for example as the maximum segments. Okay, so now we have to create an animation for this curve. So let's, for example, create a carve node, and let's animate the second U parameter. For example, let's create a keyframe at frame 1 and another one at frame 24, and also let's create a transform node, and let's create animation for the rotation of this curve. So let's say at frame 35, the value of the, let's create a keyframe for the Z value, and here let's revert it back a little, and let's create another keyframe. So here is the animation. 2 minutes. Here is the animation, and from frame 20 to 40, let's decrease the uniform scale. Okay, here is the animation. Or let me adjust this keyframe. Let's choose, let's start at frame 14. And the end at frame 40. Okay, that's good. Let's copy this animation to the points at the boundary of this animation, or the points near these boundaries. So first of all, let's create a delete node to select an area near the boundaries. So let's select point as the entity, and let's delete by expression, and let's type color red is greater than 0 and the color red is less than 0.5. Okay, let's select the delete not selected as the operation, and as you can see here, now we have the areas near the boundary of the animation. So for having a faster feedback, let's create a group, and let's name it template, and let's select only 1 point, for example, out of 50 points. Okay, and let's create a copy node, and let's choose template as the template group. Okay, here actually the point numbers change as the animation proceeds, so instead of using the point numbers here, let's go up, and right after the fuse node, let's create an attribute, and here let's create the ID attribute, which is equal to the point number. So here let's use ID instead of the point number, and here we need to create a time shift, because the length of the wire animation is only 40 frames, so we need to create a time shift. And here, with the help of the stamp expression, we can offset the animation of the wire for each point. So let's go to the stamp tab and let's enable the stamp input. Let's create a variable like CR for the red value, and let's, for example, create a PT variable, and let's create a random number based on the ID attribute. Okay, let's multiply this random number by 2, and let's type -1, so we will have a value between -1 and 1. Here let's type 40 multiplied by color red of each point, which we have access to that variable using the stamp expression. Stamp copy 1, and the name of the variable was CR, and 0 as the default value. Okay, now we have animation for each point here, actually each selected points within these templates. And the problem here is that as you can see here, we have to create a transform node to modify the orientation of the curves. And here, as you can see, the normal attribute for the points for the geometry actually is not correct, and as you can see, some of them are toward inside the geometry and some of them are pointing outward the geometry. So The problem is this Repel node. Please remember that the Repel node modifies the normal attribute of the point, so it has an easy fix. Let's create a point node and let's transfer the normal attributes from the node before the Repel node. So let's create a normal, and as the normal, let's choose the normal from the second input. So let's type nx2 and y2 and nz2. Now you can see we have proper normal attribute for the points. Okay, let's check it here. Okay, that's better. And the other problem is that now the color red value of the template points is limited to 0.5. So let's increase it to 1. So as you can see here, now we have full animation of the curve. That's good. And the other problem is the orientation of the animation. As you can see here, all the curves, they have same orientation, and the curves should be oriented according to the boundary of the animation, boundary of the geometry's animation. So what we can do here is, after the transfer node, which is responsible for transferring the color red value and starting the animation, let's create a point wrangle node, and let's create the up variable for the points, up attribute for the points. Let's connect the second input to the starting point, and let's define the up variable, which is a vector, and the up should be the position of the point, the boundary point actually. So at sign p minus the position of the starting point. So let's type point up input 2 as the input, and the variable name is position, and the point number is 0 because there is only one point connected to the second input. So as you can see here, now we have to rotate them 90 degrees along the z-axis. So now you can see we have correct orientations for the curves, and they move according to the animation of the geometry. Okay, that's good. Now what we can do here is to use this variable to randomize the orientations and rotations of these curves. So here let's use the random variable from the copy node. So let's choose plus, let's write plus 45 multiplied by stamp copy 1. The variable name is pt and the default value is 0. And also let's do the same for the rotation along the z-axis. Okay, and here we can connect the polywire node to the input geometry, and let's see the result. 0.03 should be good. And here we can create a width attribute for the points near the boundaries, so they have a less value for the width attribute. So let's create an attribute create node, and let's connect it before the polywire node. Let's create the width attribute, and the value is 0.03 multiplied by color red. Okay, and let's use this variable as the wire radius. That's good. Let's connect it to a facet node to evaluate the normals, and also let's merge it to the wire animations. And let's use wireframe to create geometry from these wires, and let's choose 0.02 as the wire radius. Here let's create a point node to add color to the points. Okay, you can see the result here, or maybe we can increase the number of template points. Maybe 10, or 1 point out of each 20 points. And also I think we can decrease the scale of the wires. Okay, that's good. So now you know how we can create this effect. As you can see, after getting the result of this digital asset, it's just a matter of playing around and creating the animation for the growth of the geometry. And you can use any method that you know for creating this kind of effect. For example, the other way of creating this kind of effect is using point clouds, and I'm sure that you can find many tutorials on creating gross animation using point clouds out there. Here I want to show you the rendered result of this animation, but before that I want to show you how you can use the output of this digital asset for the simulations. So here, for example, let's create a null node and use the output of this digital asset for the wire simulation. So usually in this type of simulations and animations, you have to have a template geometry and template animation, and then transfer the animations, deformations, or displacement to the output of this digital asset. So here let's create a simple simulation for our tube. Here let's create a dot network, and let's create a transform node before the dot network to rotate this tube along the z-axis, and let's dive inside the dot network, and here let's create a ground plane, of course let's create a gravity, and let's create a wire object and a wire solver node. Let's merge it to the static solver, and here let's use the first input as the subpath, and here let's move down the ground plane, and here is the animation using the default values for the wire object. So let's use this animation as the template, and let's transfer it to the output of the digital asset. So here we need a DOP import node, and let's import the wire object, and let's choose fetch geometry from the DOP network. Okay, so here we have only our simulated tube. Let's copy and paste this transform node and connect it to the attribute create node. So here we have the same initial transformation for the output of the digital asset and also for the input of the DOP network. And here is the idea. We have a cylinder that moves according to the simulation, and we have displacement for every point. For example, for this point, the displacement is the current position of the point minus the rest position, which is the position at frame 1. So for each point we can say that the current position will be equal to the displacement vector plus the rest position, or the position at frame 1. So let's create a wrangle node here, point wrangle node, and let's connect it to the first and the second input. Let's connect the output of the simulation to the first and the second input, and let's create a time shift, and let's use the geometry and the points at the frame 1 as the rest position, and let's connect it to the first input. Here we have to define the displacement vector, and the displacement is equal to the position of the second input minus the current position, which is the rest position. Okay, so what we have to do next is to transfer this displacement to the points of this geometry. So I want to do that using the another point wrangle node and also point cloud. So let's create another point wrangle node, and let's connect it to the first input, and let's connect the second input to our calculated displacement. So here let's create a variable for the radius, or a rod for the radius, and let's select the value like 50. Let's create another variable for the maximum points. Let's choose, for example, 10 points, and let's open our point cloud, PC open, and the texture should be our second input because it is our template geometry. So let's choose up input 2, and the position variable is P, and the variable is @P within the maximum radius and using maximum points. And we have to use PC filter to transfer the filter distance attribute. So let's transfer the distance variable to a local distance variable here. So let's define a variable here, vector, for example, template distance, and template distance is equal to point cloud filter distance. Okay, and also let's transfer the normal attribute from the template to our geometry. So let's say normal is equal to, let me copy this comment here and the variable should be normal. So, and here the position of each point is equal to position plus the temp distance, temp displacement actually. Okay, so here let's see the result. As you can see here, now you can compare this animation to our template animation. Here is our template, and here is the result after transferring the animation to our geometry. Okay, that's good, and you can see it's fairly fast. And please note that for some of the simulations, like solid simulations, you have an option to select the embedded geometry, and in this case you can select the output of the digital asset as the embedded and high resolution geometry, so it automatically transfers the simulation to the high resolution geometry. I think that's all for this video, and I'll show you the result of this gross animation, and I hope you enjoyed this tutorial, and I hope to see you in the next one.